I can't see myself having this real much for you should get a new, you should get a new. I don't know what it is. So I took the comments, it's not. That's what. And then like, yeah, it was very honest. Yeah, I got this certification.
We are going to do problem 24. Please look at this list of numbers and create a histogram out of this. Literally put them in bins. Let's say for uniformity, we'll all use a bin width of 3. So I think the lowest number might be like 5. So let's say you start from 0 to 3, 3 to 6, 6 to 9. You go all the way up to, wait, no, bin width of 3 might be 2. What's the biggest number? It's about 220. Okay. So let's say we choose bin width of 20. 0 to 20, 20 to 40, 40 to 60, go up to the highest number. Please create a histogram, and then we'll check if this data is approximately normal. Okay, problem 24. Class hasn't yet begun, it's only 2 minutes left. I'm going to go get some notes, but feel free to chit chat. And this is the page 48, chapter 2 of the 5th edition. If you have 4th, it might be different. Yeah. So please do the histogram. We'll start at 240.
Okay, from okay. Because I'm just that's what we did. Your pen is played.
That's it.
Wait, was it?
Oh, where's your pen? Oh, no. Like, where you can. Yeah.
Should be pretty. I just do something. I use that for my.
And then.
Are we supposed to be doing this next time?
No, please do it by hand. I want you to look at each number and place it in a bin. I want you to do that. There are 36 numbers, place them in each bin.
Is it on the lower side or on the higher side?
Let's say if it's 0 to 20, we'll keep the lower side. That is 0 belongs to that bin, 20 belongs to the next bin.
Okay, so 0 to 19.
Yeah.
Okay.
In fact, you can do as you wish because that will have a very small influence on the shape of the histogram. Please do this. This might be an exam problem. You are given 36 numbers. You are going to actually count and place them in bins and get it right. So look at 5. Let's say your bin list goes as 0 to 20. So this is bin number and 0. So this is the range and then the midpoint. So first bin is, let's say 0 to 20, 20 to 40, 40 to 60, and so on and so forth until, I don't know, maybe 220 to 240. Look at 5. 5 must be placed in the first bin. So have a clicker, have a 1, like +1, +1, +1, and then in the end count everything and write the total. Like maybe there is 5, 18. So 1, 2, 3, 4, 5, 6, 7, 7 numbers that are in the first bin. Make sense? And then we are looking at the second bin, 20 to 40. Maybe there are some more numbers I missed, so you do it carefully. So I'm going to keep track of this in Excel, but you can't use Excel in your exam, so please do it on paper. Okay. Does everybody or most of you have the book on your laptop so that you can see this? Oh, that's not that book. So this is the statistics text, which is for the first chapter. There's an online version that I asked you to download. If you don't have it, for now I'll keep protecting this. That book is for module 2 to 6. Oh, you have to yes. Just want to make sure the task makes sense. What you're asking. Do this carefully. So for the first bin, am I missing anything? That's 7. Thank you. 7. All right. So that's 4 plus 3, 7 plus 3, 10. 10 in the first bin. Good. Okay. I'll put 10 here. Okay. And then we are looking for 20 to 40. So there is 23. I'll use a different color for that. Damn it. Okay, 23, 25, 24, 24, oops, 24, 25, 24, then 28. That's it. Are these the only numbers between 20 and 40? Oh no, there is 33, 29. What else?
37.
37. Thank you. Turns out counting isn't easy. Okay, do we have this 3 plus 2 5, 5 plus 3 8 plus 1 9? Is everybody getting 9? Yes? Okay, so we'll enter second bin, starts at 20, ends at 40 and has 9 entries. Third bin 40 to 60. Okay, 40 to 60. Okay, so I have 40 to 60. 44, 45, 53. Only 3? Did I miss anything? No? Okay. Are we all keeping up? Okay. So 40 to 60, there are 3 entries. Yes, somebody had a question. And then next bin 60 to 80. 60 to 80. So there is, we'll include 80. Okay. 80, 65, 77, 65, yeah. Another 65, yes, thank you. 65, 70. That's it, right? So that's 5 entries. 5 entries between 60 and 80. Yes? You can do either way. I'm telling you, you can do it one way. I'll do it the opposite way. The histogram won't be different because in the big picture, it's just 1 or 2 here and there. So you can define as 0 to 20. You can say 20 belongs to the lower bin or 20 belongs to the next bin. Now we are talking 60 to 80. So for 60 to 80, we have 5. Is everybody getting that? Yes. So that's 5 entries. And then bin number 5, 80 to 100. What do we have for 80 to 100? I have 85. I already counted 80 in the lower bin, so I'm not counting it again. 80 to 100, 82, 95, 81, 92. That's 5 entries. Yes, no? 5 entries? Yes. 5. Next bin, 100 to 120. Okay. 103, 103, 110. That's it, right? 2 entries. Just 2. Agreed? The 2 entries. And then 7th bin is 120 to 140, where you have 130. That's it. Just 130. Then 8, 140 to 160. Do you see any number between 140 to 160? No, right? So next few bins are empty. 0, 9, 160 to 180. 0, 10, 180 to 200. That's also 0. And then 200 to 220. That's 1. 220 was the largest number I saw, right? So this is what 36 values, right? 36 data points. Let's see if we got that count right. So if we say sum 36. So we did count it right. It all adds up to 36. Okay. So after this point, what I'm going to do is to use Excel to kind of do some quick calculations and provide you critical values that you need to compute standard deviation. So I'm going to do part of the work and hand values back to you. You are going to compute standard deviation. Okay. So let's normalize this. This is the frequency divided by the total number. So if I normalize it, of course, what should this column add up to? This column should add up to 1, right? Because it's just normalized well. All right. Can we recall the formula for mean in terms of the normalized frequency from last class? Sample mean x bar is equal to I equals 1 to k nu I times fi normalized or relative. Nu I being the midpoint of each bin, and this is the normalized frequency, which is a fraction between 0 to 1. Okay, what is the midpoint of each bin? That's easy. I have to take the average of these two, and I just have to drag this down. Okay, so then I would write this is fi, or sorry, this is f normalized of I, and this is nu I. Can you see this better now? So let's multiply nu I times f normalized of I, which is I need to multiply this column with midpoint. Okay, if I do that, the sum of these values would be what? This is nu I times fi for each bin. If I add the sum of these values, that is our sample mean. Yes, no, yes, okay. So our sample mean is 52.22, or even I should say 52. Our sample mean is 52. First we took raw data, the 36 numbers. We literally did the binning by putting the frequency count and normalizing it. And then we got the average value 52. So here is a teachable moment. Is the answer, if I ask you what is the sample mean for this data set, is the answer 52.22 or 52.2 or 52? What do you think is the answer, the form in which you should report the answer? Why 52? Resolution. That is, we can't have some estimates which are more precise than your data. So we'll talk more about numbers and precision when we enter, the second unit. But for now, what you should understand is, if you look at the data, everything is in increments of 1. Like the resolution is 1. You don't have fractions here. You don't have 0.5 or 0.35 and so on. So when you take the average of this, you will just want to report it at the same level of precision as this original data, which is, it doesn't have any decimal point. So we'll round it off to 52. Okay. Is this making sense, or you're feeling a little lost?
What did you do with the last column in the Excel spreadsheet? That's what I would like to see.
Okay. So what I did was to take the midpoint and multiply it with the normalized frequency. And then I got that for 11 bins, and then I summed it up. This is my, I'll label it here. This is my sample mean. First part of this question is, First part of this question is represent the data in a histogram, which we just did. Okay. Second part is this histogram approximately normal? Towards the end of last lecture, we talked about what is a thumb rule check to ascertain whether this data set is normal, and that test goes something like this. Can anybody recall? So remember this bell curve, okay? Remember this bell curve. And then draw a line. This is your mean, okay? And let's say you take one standard deviation, x bar plus s and x bar minus s. If 68% lies within x bar plus minus s, if approximately 95% lies within x bar plus minus 2 standard deviations, if 99.5% lies approximately within 3 standard deviations, then this data set is approximately normal. And I told you it goes both ways. If this is true, that's normal. If that's normal, this will be true. So you are now asked, is this a histogram approximately normal? To answer that question, what else do you need? You need the standard deviation first. And then you check within one standard deviation are 68% of the values found. You need to check that. Okay. So before we do anything, let's calculate standard deviation, shall we? With me so far? Drifting? Thinking about dinner? Yeah. I'll post this. I'll post this file. I'll post the videos. Yeah. Come again?
It was B sub I times F sub I, and there was an N on top. It wasn't a power.
It was not a power. It is nu I multiplied by fi. I have to denote that this is normalized. So maybe instead of n, if it's confusing, I'll use something like a tilde. Okay, we need to compute standard deviation. Okay, so I want you to just look at your notes and see if we have a formula for standard deviation, and if so, we need to write that down first. Okay, we need a formula for standard deviation. Do we have one? So variance S squared is I equals 1 to k nu I times, fi normalized multiplied by nu I minus x sample mean squared. That's the formula. I'm going to use Excel to do the calculation, but before I do that, what does this represent? Nu I minus x bar. X bar is 52. This is x bar. When I am computing nu I minus x bar, what is that actually? It's like I'm standing here. This x bar is 52. So where will 52 come? It will come somewhere in this between 40 and 60. Sorry, if I go by midpoint, it will be between 50 and 70. So all the values before this bin will look negative when I calculate nu I minus x bar, and all these will appear positive. That is after the mean. Okay. So let me first compute that column nu I minus sample mean. That will be midpoint minus sample mean. Look at this column, tell me if this makes sense to you. That what am I doing here? If you do this on paper, you will get in your column minus 42, minus 22, minus 2, 18, 38, and so on. Tell me if you're able to make sense. If not, we'll talk. That is this part. Okay. So then we need f norm I multiplied by nu I minus sample mean the whole square. What is this? If you look at the column numbers, can you guide me what formula should I punch in? It'll be which column? G3 multiplied by I3 squared, right? G3 times I3 squared. So I have to calculate it for every bin. I forgot to write it here. Divided by n minus. Actually, this has already divided by n, right? So I'll have to multiply by n and divide by n minus. I'll write. So s squared is sigma I equals 1 to k fi ui minus x bar squared divided by n minus 1, which can also be written I equals 1 to k fi tilde, which is normalized ui minus x bar squared divided by n minus 1 times n. Kindly look at this and make sure you understand it. It's not a big concept, but I just had to multiply by n to make the calculation consistent. Yes? Hi. Is it making sense? Yeah. Is it? No, give me. Oh. Is it making sense? Okay. Yes.
So you multiply to cancel out.
Correct. This is the formula for variance. My normalized frequency already divided by n. That is not exactly what I want. So I multiply by n and then divide by n minus. Okay. So then, but if you think about it, if n is a large number like 52, 51 by 52 is almost 1. It doesn't matter. It's almost like almost close to 1. Okay. All right. So I need to sum this and multiply by n, which is 36, and divide by n minus 1, which is 36 minus 1. So that is my variance. Standard deviation. Okay, let me write that here. This is my sample variance. Okay, so if I want standard deviation, I need to get the square root of this, which will be 44. Oops, sorry. Standard deviation would be 44. Make sense?
Not really.
Tell me which step is not working.
I think it's confusing because you're asking us to do it by hand and you're using Excel, so I'm not able.
Okay, the first part when you did the binning, yes, I asked you to do by hand. once we switch to this part, I'm not asking you to do these calculations. I'm just asking you to follow with me and see the calculation roll so that you need the standard deviation so that you can perform this testing. This you are going to do by looking at the table that you made. You don't have to do anything now theoretically. Just put down your pencil and listen. Yeah. N is the total number of data points, which is 36. So this step from going from the sample mean 52 to the 44.27, which is the standard deviation, is just to get the two numbers which are needed for our calculation. Okay. Yes.
Numbers like
This one. So the question is how would I match this Excel calculation with this equation? Okay. So if you look at this equation, what is this? Normalized frequency. That is in my column G. This is mu I, that is midpoint minus the mean value. Midpoint minus the mean value. 10 minus 52 minus 42. 190 minus 52, 138. So this is just to calculate this term. Then what I do is next column, I take this value, I take the square of this value, multiply them together and write them row by row. Then I get the sum of them. Okay. And then once I get the sum, what I then do is multiply by n and n minus 1 to adjust for that difference in calculation. And then I get the square root to tell that this is the standard deviation, whereas this is the variance. This is the square root. Okay, yes.
Why did you work with normalized frequency? Why not frequency?
Frequency is something that will scale with the size of your data or whichever particular data you're using. I want to coach you to work with normalized because if I look at this normalized table, I know that between 0 to 20, 28% of the values are there. It's so intuitive, it tells you information which you will not get by looking at the raw frequency. That is why it's always best to work with normalized.
On the board, this frequency right here, that's regular frequency, not normalized, right?
This is regular or unscaled, and this is normalized. This is just a matter of opinion. I like normalized, so I preach normalized. Okay, yes.
And then the I hat, is that always going to be 1?
What is always going to be 1?
The I hat, not that one, the underneath the K.
I equals 1 to k. That's the counter.
I'm saying, is it always going to be 1?
Yeah, you can. You count from 1 to 11. So it's the counter. It's just to denote you are summing over all this. Okay. All this was just to get mean and standard deviation. Now, how would you actually check for normality? Yes. These are the conditions. You have to check whether these are obeyed or not. 2s, two times standard deviation. Let's start with this. Okay. So what is your standard deviation? 44.27. So what is 52 plus 44? 96. Okay, 96. See, it will be difficult for people at the back if you also have your own discussion. Okay, please. So 52 plus 44 is 96. What is 52 minus 44? 8. Right? So first thing you have to check is between 8 and 96, that's 68% of the data line. How will you check that? So you have here midpoints. I'm going to highlight this column and I'm going to highlight this column. I'm also going to calculate one more column where I take this. I also will take this and add it to the previous row so that I get something like a cumulative frequency. Okay. So what I'm asking you to check is between 8 and 96, does 68% of the data lie? 8 doesn't appear here. The closest we have is 10. 96 doesn't appear here. The closest we have is 90. So you have something like between 10 and 90, you have about what? Should we take all of these or should we take 0.88 minus 0.27? I leave it to you. Think and tell me, should we consider that between 10 and 90 we have 0.28 minus 0.88 or 0.89 minus 0.28, or should we just think 90% of the data lies between 10 and 90? Yes.
Well, the bed itself has values that are below 10, above 90, right? So you have to subtract.
So you're saying you have to subtract?
I think so.
Okay. Anyone else has other like choices, or you think that is right? Yes.
That's the question.
Question is, you have midpoint 10 and then midpoint 90. So should you just take the end values and subtract them so that it's 0.89 minus 0.28, or should you just think 90% of the values lie between 10 to 90?
It's like most of the numbers are there. When you get toward the end, you only have two numbers, like 4 numbers that are outside of the two.
Okay, let me explain. The other problem is when people ask questions, I saw the recording, the questions don't show up because their voice is often low. So that's another reason I really request you not to talk, because on the recording, those questions are not coming up. Okay. So let me try to explain this. Here's your histogram. It's a very weird histogram if you think about it. Take this midpoint and let's make a graph of midpoint versus normalized frequency. Okay, let's see how it looks. One second. Okay, so we have frequency, delete this. Yeah, okay. So the histogram looks something like this. A lot of the values appear in the lowest bin. It then has a secondary peak and then it goes to 0 except for one value at D. Okay. So if you want to know how much of the values lie between 8 and 96, you have to first recognize 8 and 96 don't appear on this histogram. They are not within the resolution. So we have 10, 30, 10, 30, and so on and so forth. So we'll consider 8 approximately as 10. And then we'll consider 96 is approximately 90, because that's the closest we have. Are you with me so far? Okay. So it's like translating from 8 to 96, we are asking how much of the data lies between 10 and 90. So you shouldn't count what is already at 10. You should take whatever is at 90 and remove the contribution of whatever is at 10 and basically take the difference between 0.88 and 0.27. So the difference of these two values would be the percentage of data that lies between 10 and 90, or in other words, 8 and 96. Is this making sense? You are not going to get data that always looks very convincingly normal. It will be kind of these very ambiguous data sets, but you have to understand how to make judgments. If 8 is not appearing on your list, you shouldn't seize. You should think what's closest to 8. 10. 96 is not appearing. What's closest? 90. Okay. So we would say 0.89 minus 0.27, which is how much? So if I say 0.888 minus 0.27, about 61% of the data lies between plus minus 1 standard deviation. Yes.
Isn't 100 closer to 96 than? So
That is not a midpoint. Next midpoint is 110.
gotcha.
That's why I went for 9. And you can see how subjective this is. If this were not 96, but let's say 107, I would have chosen 110. So this becomes quite as much as an art form as a science. Okay, so you have to kind of know how to make it. Okay, with me? Still thinking about dinner? Okay, yes.
I just don't understand why we're subtracting the 0.8 minus the 0.6.
Oh, that's because we are asking the question, how much of it lies between 8 and 96? We don't want to know what is before 8. We want to know only what is between 8 and 96. That's why we are taking what is at 96 and what is at 8 and getting what lies between them. Okay, is that okay? So what I would then suggest is, since I've spent enough time on this, I would ask you to check the remaining two conditions as well, the x plus or minus 2s and 3s, and see how well it actually obeys it. In the conclusion, what you will find is that so if you say x plus or minus s, what is the target number? 68%. We have only 61%. 61%. Okay. And then x plus or minus 2s, the target number is 95%. You find out what is. It will probably be 100%. When you do the calculation, you will see. So what you're going to find is, even though it kind of obeys in a upper limit sense, this data isn't exactly normal. Okay. And as practice problems, what I would suggest you to do is look for similar values. Sorry, look for similar data sets. Like if you see problem 25, they have given you a histogram. Sorry, not a histogram. They have given you the values in each bin. They are asking you to compute everything that I did. Sample mean, standard deviation, is the data approximately normal? I will save this file and post it on Canvas. If you want, you can use it, or you can create your own file and practice. Okay. In the exam, this kind of a problem will, if it appears, it will have this table provided to you. You don't have to do any of the hand calculations. You will be basically given the histogram, the sample mean, and the standard deviation, and you have to go through this calculation and check. Basically, if I had given you the normalized frequency, you should be able to check from there on. Okay. All right. Any questions? Is it so easy, so straightforward, or is it so difficult that you just gave up? Yeah. That based on the way this data looks, if you take 2 standard deviations, it will be so broad that all the data will lie within it, is my guess. Yes, 52 plus 88, and then 52 minus 88. So all but the last data point will fall within that. That's just 1 out of 36. What is the fraction of 1 out of 36? So 1 out of 36 is that's 2.7%. So about, it's like almost saying 98% of the data will lie between this. Yeah. Okay, so let's move on to the next idea. Yes. Okay, that's a good question. If it strongly satisfies the first, but doesn't really meet the second two, or it is kind of ambiguous, it probably is a normal distribution. But if it fails squarely in the first condition, it's probably not a normal distribution. The reason the first condition is so important, because this is where most of the data is. This is where you have a lot of reliability. You have more observations there to make a decision. As you go further, 2 standard deviations, 3, 4, 6 standard deviations, you are essentially looking at the fringes. It is called fringe for a reason. It's so out there that you call it a fringe. So the reliability goes down as you go down to further standard deviations. So if it fails here, it probably isn't. But if it passes here and starts failing later, maybe there is a chance it is still a normal distribution. Hope that makes sense. Okay, so the next idea I want to introduce is most often we have data paired data sets, like quantities that kind of have a relationship with each other. So when you look at a graph, like when you see something, I'm going to turn this off probably. Okay, so when you see a graph, let's say you have some quantity x and some quantity y, what is a graph usually a representative of? It tells the relationship between the two variables, right? So if we draw a straight line, or if we draw a straight line, what is the immediate implication? What do we say in plain words? They have a linear relationship, right? Or if you draw a flat line, what does that say in plain words? They are practically independent. That is, this variable can change, but that does not lead to a change in this variable. That's what it means, right? So this is apparent when you draw a graph, and when the trend is very clear. It's either an unambiguous flat line or a straight line or some kind of a curve. Now, what happens when you have data that you are given a table of, let's say, x and y, and you plot them? It sort of looks wishy-washy, meaning it's very noisy. There are lots of values. It's clustering. It's kind of given like this. How do you say whether this data set, these two variables actually have a relationship with each other, or they are practically uncorrelated? In the sense, is it this or is it this? Which is it? How do you ascertain correlation? That's the question. Exactly. How do you, one second, how do you ascertain correlation? Okay. What was your answer?
That's it.
So line of best fit works when your data is not very noisy. You have something that looks, let's say, you have data points that go like this. You can fit a second order or a third order curve, and you can do perfect. It's neat. You will get, probably you're aware of this. You will get a term called R squared, which tells you whether the fit is good or not. If it's close to 1, it's a good fit. You've done this in Excel, right? We are basically trying to understand what that R squared means. So we want to calculate a parameter called a correlation parameter. We'll call it R. Okay, call it R to tell us whether two variables have a correlation. And this parameter is defined such that if R is 0 or R is either R is 0 or R is very close to 0, that means they have no correlation. And if R is 1, it means they have a positive correlation, meaning they both increase together. And if R goes to -1, meaning they have a negative correlation, meaning as one increases, the other decreases. So this could be values that you collect from an experiment or quantities that are measured together. Just because you measure them together, that doesn't mean that they have a relationship with each other. That is what we are trying to understand through this correlation parameter. It's an ugly, messy formula. Okay, so I'm going to write it here. So if you have paired data, let's say you have xi, yi, you have x1, y1, x2, y2, up to xn, yn. N pairs of data points, x and y. If you have that, then we define correlation coefficient. This definition is given in page 37, just in case I scoop up some formula. Page 37. R is equal to summation I equals 1 to n xi minus x bar yi minus y bar divided by summation of I equals 1 to n xi minus x bar squared yi whole thing under the square. One second. So obviously doing this R calculation without a Excel or a MATLAB is not very convenient. It's not the point. I'm not going to make you do this calculation. But what I want you to understand is by looking at the value of R, whether it is closer to 0 or closer to 1 or -1, I want you to be able to understand the correlation between variables. The other thing is, when you look at a graph, yes, you had a question?
Is that a whole thing like one fraction?
Yes. So when you're done writing, I'm going to bring back the screen and show you some graphs and R values, which tell you how the variables are correlated. Okay. So the exam question on this particular idea is, you will be shown a graph and asked to say whether the R value is close to 0, negative or positive. Make sense? You should be able to look at the graph and tell the R value, or look at the R value and tell how the graph will look like. Okay. All right. Okay, so let's look at these. you look at a value for R equal to 0. Look at the graph on the right side. This is how data looks like. It won't be a nice and straight horizontal line for you to immediately recognize it. But what is, you look at this data, what do you get from it? The two variables. So it's, if you just make a qualitative argument, for large values of X, there are large values of Y. For small values of X, there are large values of Y. For small values of X, there are large values of Y, or small values of Y. For small values of X, for large values of X, there is also large Y. From this, what do you correlate? Nothing. You can't make any conclusion about this data because either way, there is no trend that can be generalized. Okay. Forgot to bring it, but I don't know if you guys have seen this. There is this countries or wealth of countries divided by the energy output of energy produced by those countries. You can go check this on the internet. There are no rich countries that don't produce a lot of energy. Correlation is, if you produce a lot of energy, you will eventually become rich. That's what the data says. There are no poor countries that produce a lot of energy. There are rich countries that don't produce energy, but there are no poor countries that produce a lot of energy. Okay. So look at the next graph here, minus 0.5. What is the difference between 0 and minus 0.5 that you can visually see? Yes. There is a sense of direction here, although there is a scatter, but there is still a downward trend, correct? That's what you can immediately see. The thumb rule test is you should be able to take a ruler, make a line through that, and the data, most of the data should pass through that line. That's the rule of thumb. This is unmistakable, right? 0.9. There's a clear upward slope. There is some scatter, but it's not back. It's unmistakable. So when you are in the business of publishing journal articles, if the editor knows you, if your reviewers know you, they take these kind of wishy-washy correlations and call it, oh yeah, that's a perfect confirmation of this experiment or whatever, which is what you should not do. You should, unless your data looks like this, you shouldn't say it's very clear. In fact, this is sort of ambiguous. Okay. Yes.
So the negative.
Yes. 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 Negative sign basically means slope. You are closer to 1 means there is a clear relationship. Closer to 0 means there is almost no relationship. So this little section here, I would definitely ask you to read. It's for your own good, that you don't confuse correlation with causation. Just because two things are measured together, that doesn't mean one causes the other. Okay, so take a read at this paragraph. I'll leave it to you as homework. Okay. All right. So that sort of concludes chapter 2. Questions before I move on to the next topic? It is 40. So there was also a question that I got in an email. A student had asked, when is the time to study the assigned reading? The answer to that question is, you have the lecture schedule in the syllabus, right? So just before the next unit is about to start, do the reading for that chapter. So for statistics, the ideal time would have been before the first class, but it's okay, you can still read now. But for the module 2, before, let's say I finish statistics today and I know on Tuesday I'm going to start module 2, you would probably read it over the weekend. Okay. And the other question was, when do we do problems? So today I finished the discussion on chapter 2, the topics I listed there. So this is now a good time to do problems on chapter 2. There is chapter 2 of module 1, which is statistics. There is also a little bit of chapter 3, 4, and so on. So the thing with this practice problems is you want to do at least 4 or 5 problems of each type. Like if finding out if a data set is normal, we did 1 problem, you should probably aim to do 4 more at least. If we want to do correlation coefficient, looking at bunch of graphs, you should aim to do at least a few problems. Okay.
Is there an answer key to the book for the problems in there?
I'm sure there is a key. I don't have it, but yeah. Okay, so let's move on to the next topic. I want to ask the question, what is a random variable? What is your understanding of the phrase random variable? That can assume random values pretty much. So whenever you take either physical processes, natural processes, or quantities that have a lot of variability, like if I take the height of the people in this room, obviously not everyone's going to be of the same height. There is some variability person to person. The height, if we denote it as x or whatever, x is a random variable which has some distribution according to the height of this people in this room. So when it comes to random variables, we classify them broadly into 2 kinds. There are those that are discrete and then those that are continuous. Height of a person, is it a discrete random variable or a continuous random? Continuous, right? Because you can measure height to, like it's a real number. You can measure it like 1 inch, 1.1 inch, 1.01 inch, and so on. Can you think of a variable, random variable, which is countable and discrete? It's like in specific values.
On the dice.
Roll of a dice, the outcomes are like 1, 2, 3, 4, 5, 6. What else? Oh, can you elaborate? I mean, number of people, anything, number of anything is a countable thing, but you have to give context. Okay, that's 2 ways. Let me try to give an example. If you take a certain geographic region, like let's say San Francisco Bay, they say the average rate of earthquakes is once every 30 years. Okay, or you can say the average is 1 divided by 30 as a fraction in number per year. So I'll write it as average is 1 divided by 30, or that is 1 quakes every 30 years. What does that mean? That's about 0.033 quakes per year. Obviously, there's no such thing as a 0.033 quakes, right? But if you happen to live there for a few years, 20 years, 30 years, whatever years, what are the odds that you will experience 2 earthquakes or 1 earthquake or 4 earthquakes? That number of earthquakes is a variable that is discrete. That is the random variable. That is, let's say I live there for 4 years, you live there for 5 years. Do we both experience the same number of quakes? Probably not, right? Or maybe 2. So the number of earthquakes is a random variable and a discrete random variable at that. And height of a person is a what? Continuous random variable. Okay, good. So let's talk about some other ideas. So when you take a dice, a dice can provide 2 outcomes. Either it can assume head or tail, or you say 0 or 1. Obviously, this is a discrete random variable, right? What is the size of the sample space? What are the total number of possible outcomes? 2, right? 2. So the probability is either 1 over 2 for either 0 or 1. That is either head or tail. And you can easily make, sorry, this is a coin, not a coin. Keep mixing this. So dice, you have 1, 2, 3, 4, 5, 6. And the probability is, if it's a unbiased die, it's 1/6. Right? The outcome that you want, divide by the total number of possible. Yeah.
Yes.
Okay. We should all see your faces. I mean, I get that puzzled look, so I get shaken. I ask you, are you okay? Am I doing something wrong? Okay, so let's introduce a concept. What is the probability? What is the probability of getting a head or a tail? 100%. Either it is 1/2 or another 1/2, which makes it 1, right? And it's like asking, what is the chance if I roll a dice? What is the chance that I'll get a number, any number? 100%, right? So a discrete random variable that can assume a set of possible values, and this set may be bounded or unbounded. Like for example, the coin can assume 2 states, the dice can assume 6 states, which are bounded numbers. What is the number of earthquakes in theory? If you live there for 100 years, in theory, can you experience like 500 earthquakes, 800, 1000? In theory, this can go on and on, right? There is no bound to this. So whether it is bounded or unbounded, that's okay. Bounded or unbounded. A discrete random variable that assumes a set of possible values for a discrete random variable that assumes a set of possible values. The sum of all the outcomes, the sum of the probability of all the outcomes is 1 or unity. So it's like writing I equals 1 to m, pi equal to 1. Okay, where m could be a finite number or m could be infinite. Okay. So the first idea is the sum of all the outcomes must lead to a total probability of 100%. It's almost like stating the obvious, right? You agree? Yeah. Okay. So then the average value or the expected or expectation for the random variable is, okay. So let's say this random variable can take states xi, that is I equals 1, 2, 3 up to m. And for each of those xi values, the probability is pi. For the case of coin, what is xi? We'll call it 0. Head, we'll call it 0. What is the probability of what is it? Sorry, xi Pi. If xi is 0, probability is half. If xi is 1, the probability is half. Okay. For the dice, you have xi, Pi, 1, 2, 3, 4, 5, 6, 1, 6, 1, 6, 1, 6, 1, 6. Okay. So what is the average value of the value? Oh, sorry, what is the average value when you throw a dice? That's the question. So the average value would be x bar is summation I equals 1 to m xi pi. Can you do that? In this case, for the dice, what is m? How many outcomes? 6. 6 outcomes. Each value has a probability of 1/6, so it's almost constant for everything. And then you are going to write 1 over 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. How much is this?
3.5.
3.5. Thank you. It's like saying whenever I throw dice, I can expect an average of 3.5. That statement is a funny statement because you know that you can't get 3.5 on a dice. So what is the interpretation of that statement? Please say it loud.
It's normally 3 or 4.
It's most likely to be 3 or 4. So if you are in a casino and betting money, you would put money between 3 and 4. And if you keep doing this statistically, you would do better than putting it anywhere else. Like let's say you keep betting 6 all the time. You are only going to do 1/6, or you're going to win only 1/6 of the time. But if you are going to keep betting 3 or 4 all the time, you are going to win 1/3 of the time. Okay, pick 3 or 4, just bet on it. You're going to be successful 1/3 of the time. That's the interpretation. It's not an endorsement for gambling. For all the financial types out there, if you want to do well in stock trading and predicting and everything and AI, learn statistics. It's all statistics. Those guys are they are not just money people. They are actually extremely good mathematicians. They just don't look that way. Okay, so that is the expectation, which is a very commonly used value. Okay, we'll define expectation and standard deviation again for continuous variables, but the idea is, okay, let's talk about one more example. So I talked about the number of earthquakes per year, okay, or per 30 years. That is one. I told you roughly they expect a quake every 30 years in the San Francisco region. Okay, so the question for you is, if you live there for 15 years, what are the chances? What are the probabilities of experiencing this is number of quakes, this is probability. Okay. What are the possible values number of quakes can take? Can't be negative, right? It has to be starting from 0, right? It can be 0 quakes. You can live there for 15 years, never see a quake. So 0, 1, 2, 3, it can be quite large. It can theoretically assume any number, right? But that doesn't make it likely. What is likely is the height of the probability that we can calculate or estimate. So I'll call this PI and I'll call this I. Okay. So what is the average number of quakes we will experience? How will you compute average? Actually, there is a little bit of trick and detail in how this probabilities come. That is the subject of Poisson distribution. We'll get there. But at least with this information given to you, how will you estimate the number of quakes? Average number of quakes. No, that is the rate at which it happens, and that number usually comes from historical data. They take 200 years of data. If you had, let's say 210 years, and you had 7 quakes. So they take 7 divided by 210, come up with the average, it's 1 every 30. But that doesn't mean every 30 years there will be a quake, or it could be spaced together, far apart, right? So if these are the probabilities, my first question to you is, how will you compute average? Yes. In that 15 years, the rate is 1 every 30 years. And let's say for 15 years, we were able to estimate these probabilities. These are given to you. How did I estimate these probabilities? We'll get to it in a future, maybe next lecture. But right now, just take these probabilities from me. And I'm asking you, how will you compute the average number of quakes in 15 years? I want you to just think about how you will apply this formula or generalize this formula for this situation. Louder, please. Can you be louder?
You add probabilities and then divide weights.
Okay, let me suggest something else. First thing is, the number of quakes can assume values that are 0, 1, 2, 3, 4, 5, 6, right? This is equivalent to the number that appears on your dice. That is, the dice can assume values 1, 2, 3, 4, 5, 6. Your quakes can assume values starting from 0 onwards. But what's the big difference between the dice, number of outcomes in dice, and quakes?
The probability of earthquakes is not as evenly distributed as the dice is.
It's non-uniform. Good. What did you want to say?
I was going to say that.
It's non-uniform. That's a good observation because I didn't draw the peaks all the same height. Not only that, this is bounded. There are only 6 outcomes. This is not. This can have any number of outcomes. I said that doesn't make all of them probable, but they are possible. Okay. So if you want to write the average number of quakes, I'll call it I bar. Okay. The average number of quakes is the number that you are looking at multiplied by the probability of the number actually happening. So I equal to 0. What's the upper bound of I? Should I put 4, 5, 6 or infinity?
I guess, or in this case,
I mean, let's say I can keep on calculating, but it will keep diminishing. But in theory, it goes up to infinity. That is, it is the number of possible outcomes. So this is the possible outcomes. Possible outcomes. This is the probability of those outcomes. If something is very low probability, what will be the value? 0, right? It will go to 0 pretty quickly. Okay. I just wanted to give this as an example of a bounded set and an unbounded set. Yes.
Where do you get the possible outcomes from?
So if I'm thinking about earthquakes, it can be 0, 1, 2. It's just a like it's obvious that it can only be integer, right? You can't have 1.5 earthquakes. So it's just a how do I say this? Self-evident truth.
I was just wondering where it came from. If you were doing like the real, where would you get that?
It depends on the context. Like for example, if you think of the lifespan of a bulb that's measured in hours, that is a number which is going to be continuous. It can be 40.1 or 35.4 something. This is a quantity where it is number of earthquakes, which can only be an integer number, but there is no limit to what integer it can be. It can be 4, 5, 6, 7, and so on. Whereas the dice has only 6 faces, so it has to be 1 to 6. Yes, there is no definite upper limit. That's what makes it unbounded. Yeah, it doesn't contribute to the average, but others will. So suppose the probability of others are really tiny, and you have 0 as the tallest skyscraper, your average will be very close to 0. That's what that means.
But that just won't contribute to any of it.
So it's like asking if let's say this is 30 years, right? This measurement is for 1 every 30 years. Let's say you live there only for 1 year. Obviously, the odds are low for you to experience a lot of quakes. So these higher probabilities will be naturally close to 0, whereas the chance of you getting away without any quake is the highest. So this will scale with the time you spend there, and we'll see this when we do Poisson distribution. Okay, so whatever I've discussed so far, you can find that in section 4.1. So until now, what I have discussed regarding random variables can be seen in section 4.1. Now we want to discuss the next idea, which is okay. So we talked about probability. We call it P of xi or Pi. It is the chance that the random variable x assumes a value of xi. Okay. So I keep going back to those familiar examples. Let's say for the dice. Okay. If I were to draw P of xi versus xi, I have 1, 2, 3, 4, 5, 6. How will this graph look like? Probability versus the value of the random variable for the dice. It will be the same value for all the x values because the probability is the same. right? This is for a, let's say we'll call it an unbiased die. But again, going back to the gambling example, if you rig your dice and let's say you machine off one side such that it's lighter or it keeps falling more often, that's a way to bias the die and get a certain outcome more than the other. Okay, so in that case, the levels will be different. Okay. So the another quantity of interest this is probability of x assuming xi, which is 1/6. So let me ask you, what is the probability that x assumes values that are equal to or less than 3? How will you say the values? When you roll the dice, what are the odds it will be a 3 or less? It will be 1/2. More importantly, there are 3 favorable outcomes. That is the probability of x equals 1 plus the probability of x equals 2 plus the probability of x equals 3, which is 1/6, 1/6, 1/6, 1/2. Okay. So this idea, what is the probability that x is less than or equal to 6? Just tell me quickly. 1, right? That's just 1. So this value where we define a function f equals x is the probability of x assuming values that are equal to or less than x. This value is called cumulative probability. So if I ask you to graph cumulative probability on here, f of xi, how will that look like? That is, you have to keep, when you are at 1, you have to ask what is the value of it assuming 1 or less, which is just 1, right? So the value will look something like this. When you are at 2, you have to ask the question, what is the probability of the die assuming a value 2 or less? What is that value? 1/3, right? 2 favorable outcomes out of 6. So that's 1/3. So if this is 1/6, this is also 1/6, but then you have to jump to 1/3. And at 3, what is the value? 1/2. So I'll just write it because I don't have time to draw this. So this is f of x, f of 1 equals 1/6, f of 2 equals 1/3, f of 3 equals 1/2. What is f of 4? 2/3. And 5/6. Then 100. Okay. So in addition to probability, we also want to look at cumulative probability because it has a lot of utility when doing quick calculations. Okay. So we'll continue on Tuesday. So 2 announcements. One is, if storm doesn't stop us, we are on schedule for the prerequisite quiz. We'll start at 2:40. If campus is closed, we will move online and just have a regular lecture through Teams. I'll send the link. The quiz will be the next time we meet in class. If it is Thursday, hopefully. Okay? Yes.
So I saw the put two assignments in. The first one was the math information, the second was an Excel. How do we verify that on the Excel?
I don't verify. I trust you.
Okay. But there's a fill in the box to submit. There's just a on
You just write. You just take a piece of paper and say, "I confirm that I have watched the Excel video."
Make sure put it in there. Thank you. Yeah. I believe